Okay, so this is our final video for this week, week 8. So let's see, we have a differential equation governing the displacement of a damped oscillator. I should probably say harmonic oscillator, because this is like a kx, it's a Hooke's law, but anyway. Solve the differential equation using only Laplace transform. So as usual, I'd like you to have a look at the back of your manual and look at the table. So we're going to be sending a second derivative, a first derivative, little x, and 0. So if you look at the back of your table, for x double dashed, so the back of your manual, look at your table, the x double dashed is like the f double dashed, second derivative, and we send it, and the role of f in the formula in the tables is played by x. Okay, so the tables say that a second derivative is sent to s squared. Now the tables then says big F of s, but we're using x, so instead of big F, it's big X. Then the table says minus s times, it says f of 0, but for us it's little f of 0, so for us it's little x of 0. And then the formula says little f dashed of 0, so for us that's little x dashed of 0. So that's the second derivative gets sent to this, plus twice. Now this x dashed is like the f dashed, and if you look at the back of your manual in the table, it's sent to s times big F, but here it's big X, minus little f in the tables, of course for us is little x. As written, this is not good. According to Bandas, you need a bracket here. That is important. Then next term, now we're doing it term by term, fixing constants because the Laplace transform is linear. So fix the 10, and little x of t gets sent to big X of s, and 0 is a constant. Do send it, even though after a while you might recognize that it always gets sent to 0, but if it's a 1, it's not sent to 1. 0 is sent to 0 over s, because it's a constant. That's the first thing. Second thing is apply the initial conditions. So that's these little x's will be in the question. So we have s squared times big X of s minus s times x of 0. X of 0 is equal to 0, so nothing there. Minus x dashed of 0. X dashed of 0 is equal to 1. Plus twice s times big X of 0 minus little x of 0, and little x of 0 is 0. The more zeros the merrier. Plus 10 times big X of s equal to 0. Right. So we're going to tidy this up, and I haven't left a whole lot of space, so this is just a remark for myself to leave more space for next year. Okay, so what I'm going to do is multiply out first of all. I get s squared times big X of s. S times 0 is just 0, so forget about that, minus 1, plus 2 times s times x of s. 2 by minus 0 is just 0, forget about that, plus 10 times x of s is equal to 0. Now you're trying to solve this for big X of s, so what you want to do is you want to get everything that isn't x of s out of there, in particular this plus 1. So I'm going to add 1 to both sides, and just because of space I'm also going to take out, so I'm going to add 1 to both sides, and then I'm going to take out x of s as a common factor. And that should give me, take out the x of s, therefore s squared, this minus 1 is going to be gone because we're adding 1 to both sides, plus 2s plus 10 equal to 1. And then if we're trying to solve for x of s and it's multiplied by this quadratic, we need to divide both sides by that quadratic. So we're dividing both sides by s squared plus 2s plus 10. So we're getting x of s is equal to 1 divided by s squared plus 2s plus 10. And that is the beauty of this Laplace transforms. It's easy to solve for the Laplace transform of the solution, but now the problem comes in, we have to send this thing back. Okay, so you look in the tables, and maybe at the moment the only thing this possibly looks like is, if you have a good look in the tables, maybe have a think, what you might notice is it looks like omega divided by s squared plus omega squared, which is a sine omega t. Now, it's not exactly a sine omega t though, because of this plus 2. So the suggestion is, okay, maybe this isn't one of these. I can maybe write this as a sum of simple terms. Now, I've written this a number of times. Write it as a sum of simple terms. That's called doing the partial fraction expansion. So partial fractions is what we need to do now, and the very first step with partial fractions is to factorize the bottom. Now, if you try and factorize the bottom with the AC method, 1 by 10 is 10, and look at all the factors of 10, you get 1 by 10, 2 by 5, 3 doesn't go, 4 doesn't go, 5 you already have. You cannot make up plus 2. So this means that this factoring using whole numbers is not possible. It might still be possible to factorize it using what are called surds with square roots. So what you have to do is you have to say, okay, I'll find the roots, and I know that roots correspond to factors. We've seen this in a previous video. So yeah, we'll go and find the roots. Now, particularly in this module, you're going to suspect when you can't factorize it that actually it doesn't have real roots. It doesn't have real number roots. The roots are complex numbers. And when that happens, well, you can't factorize it, because no real roots, no real factors, because always roots correspond to factors. And if you have a real factor, you have a real root. So if there's no real roots, there's no real factors. So what you want to see does it have real roots is you just look at the thing inside the square root. Because remember, the square root of a negative number, and I can just put in, say, -1, this is not a real number. It's an imaginary number, which we did use in chapter 2, but here we won't be using directly. So we need to look at the thing inside the square root in the minus b formula, which is b squared minus 4ac. And with this example, the b is 2, the a is 1, the c is 10. We get 4 minus 40, which is minus 36, which is negative. Square root of minus 36 is not a real number. No real roots, no real factors. We've said this a few times. No real roots, therefore no real factors. Now, that's bad, because, okay, what does it mean in terms of the partial fractions? It means that you've got a rule 3. But if you look at it, you can't simplify this anymore. I mean, if you write out what the rule 3 is, you get, oh, bs plus c over this. Well, it's already done. The b is 0, there's no s's, and the c is 1. So the partial fraction expansion doesn't give us anything. That's not great. Okay, so you're looking again at this, and you're saying, okay, maybe this is the only game in town now, because you can't do partial fractions. So is it possible maybe that I have a sign but shifted? So instead of s, I've got s plus a. I know I've written this really awkwardly. So suppose I got omega over s squared plus omega squared, but the s is shifted to s plus a. That maybe s squared plus 2s plus 10 is actually equal to s plus something all squared plus omega squared. Can I do that? So you end up with s squared plus 2s plus 10 equal to s plus a, that's the shifting, will be the shifting, and a shifted s plus omega squared. Now we're going to multiply out the right hand side and compare. We might just mention something that I've just recently thought of. One thing you could actually do here is generate equations in a and omega by substituting values of s into both sides. It's not the stupidest thing I've ever thought of. So for example, if you substitute 0 into both sides, you get a squared plus omega squared must equal 10. The question then is to pick another clever value of a or s. Now you could put in minus a. Maybe this doesn't work as good as I think it does. No, it doesn't actually. It is possible. No, it doesn't really work. Okay, I'm sure there's a way of doing it. So what I'm getting at is with the partial fractions, when you're trying to force two things to be equal to each other, you substitute in values of s, and you keep you can just generate equations in the a and the b. Here we're going to compare coefficients. So compare coefficients means multiply out the right hand side. If you do this carefully, s plus a by s plus a, you get s squared plus 2as plus a squared plus omega squared, and now compare these. Now they both have an s squared, that's good. What's the coefficient of s on the left? Now the coefficient is the number multiplying s. Well, what's multiplying s on the left is 2. And what's multiplying s on the right is 2a. I want those to be equal, and I also want the constants to be equal. So the two constants that I have are 10 and a squared plus omega squared. And if I can find a and omega such that 2a is equal to 2 and a squared plus omega squared is equal to 10, I'm done. So this is two little equations. So the first one says 2a must equal to 2. So you've got a multiplied by 2. You want to get a on its own. The inverse of multiplying by 2 is dividing by 2. So I divide both sides by 2 and I get a is equal to 2 divided by 2 is 1. And then I also have a squared plus omega squared is equal to 10. Now the good news here is I already know what a squared is. It's 1 and 1 squared is 1. So I have 1 plus omega squared is equal to 10. Then I'm going to take away 1 from both sides and I'm going to get omega squared is equal to 9. Then I'm going to take square root. Now just before I take the square root, we're going to be careful. In general, if you have squares, hopefully that wasn't missing, you have two solutions. So we're going to have two solutions here. So I do the square root of both sides, you get omega is equal to the square root of 9. Where are the two solutions? Well, plus or minus. So minus 3 squared, that's minus 3 by minus 3, also gives you 9. So there's two solutions here. You can, if you're a bit weird, do it with the negative one. Trust me, don't throw out the negative one and do it with plus square root of 9, which is 3. If you really want, you can do it with minus 3. You get the same answer, but it looks different. Okay, so what that means is this s squared plus 2s plus 10, if we force it to equal s plus a squared all squared plus omega squared, the a must be 1 and the omega must be 3. So this big x of s that we found back here, the easy thing, we said, okay, it's a shifted sign we got to here. And we'll see what I've written on the next page. So we have this here. I think it'll be written again on the next page. Right. So we're thinking it looks a little bit like a shifted sign. Right. So what I've got written here, okay, shifted cosines. Now there's no s on top of this. It's a 1. So it's definitely not a shifted cosine. There's no s there. So that's not a problem. I don't even know why I've included that. But anyway, you might be looking. But the shifted signs look like omega over s plus a squared plus omega squared. So in our example where the omega, now you look at this to be the omega, you want to look at this as the more important thing. You can't really change that. We can mess around with that. This really is your omega. Omega is equal to 3. Oh, we have that up there as well. Yeah, it's no mistake that this is also the omega. The omega is equal to 3. So a shifted sine 3t looks like this with the 3 on top. We do not have the 3 on top. What I'm going to do is I'm going to write the x of s again. I'm going to write the +1 shifting in red just to highlight it. So if x of s is equal to, now actually I'm not going to write the 1 error, I'll write it here. 1, and actually I don't have to worry about putting the shifting in red yet. Okay, so two things. First of all, I want a 3 on top here. Now what you do is if you know how to balance the books, you can just throw a 3 there. Throw this in green. Put a 3, that's what I want. Okay. I'm also going to put the shifting in red. And I've got plus 3 squared. Now, what's written here is not good because this equals is not justified. I've got x of s and suddenly I've got 3 times x of s. So these things are not the same. But what you can say is to balance the books, multiplying by 3, which what we did, you can balance the books by dividing by 3. And dividing by 3 is the same as multiplying by 1/3. And this 3 divided by 3 is the same as this 1. And now we are ready to send this back. We may as well just write down the first shift theorem. This is in the tables. It says that when you have a Laplace transform of something and the s is shifted to s plus a, that what you do is you bring it back as normal, as if it wasn't shifted at all, but then you multiply it by the exponential shift. So if this is a plus a, you multiply by e to the minus at. This first shift theorem is in the tables. So what we have here is, suppose the s plus 1 wasn't there. This is an omega over s squared plus omega squared, which we would have written back on the previous page, which I'll just go back to here. So without this shifting, omega over s squared plus omega squared, that's a sine. And it's a sine 3t. Look in the tables, sure. We may as well, I have to take this away to write it. So the tables also say that omega over s squared plus omega squared goes back to sine omega t. Now obviously to get used to all these patterns you have to be doing the questions yourself rather than watching me. But anyway, so here this thing is like a omega over s squared plus omega squared, where omega is 3. It's going to go back to sine 3t, well 1/3 sine 3t, except it's shifted. So this pencil bit says if it's shifted, bring it back as normal. So we're going to bring back the 1/3 sine 3t, but then multiply by this shift e to the minus at, and the a for us is 1. So we go back from big X of s, apply the Laplace, inverse Laplace transform, we get little x of t, fix the 1/3, and then as we said, bring it back as if it isn't shifted. It'll go back to sine 3t, and then multiply by the exponential shift. Because it's a plus 1, it'll be e to the minus 1t, and minus 1t is minus t. And then at this stage, and we'll have a video about it next week, just to definitely recognize what type of damping you have, this is underdamped. It's underdamped because there's an oscillation, which means if there is a door frame, it wants to oscillate, it'll slam. That means the damping is not strong enough to slow it down. It is under damped.